Hello. Okay, so I will start my today's coding practice. So today's question is a quite famous one, which is named find median from data stream. I actually know the solution of this. I use the two heaps. Yeah, but yeah, in today's practice, I will explain it clearly and explicitly, and I will try to write the test code. Yeah, and so on. Okay, so that being said, I will start my practice. So this is question. So the median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value. And the median is the mean of two middle values. Yeah. For example, for array 2, 3, 4, find median 3. And for array 2, 3, the median is 2 plus, because there are two numbers which is even, the median should be the middle two numbers, average of middle two numbers 2 and 3, which is 2.5. Okay. And in this question, I will implement the median finder class, which is these methods. The first method is median finder. Oh, yeah, this is actually the constructor. Okay. And the second method is addNum method. So which adds integer num from data stream to the data structure. Okay. And the final one is double, find median method, which returns the median, okay, of all elements of answers within, okay. Okay, so okay. So in this question, the numbers are input as the data stream. So it is not like I will be given the array and find the median from that array. If it's the case, I just have to sort the array and find the middle index number or maybe numbers and get the median. However, because this is the data, the input is the data stream, I can use that way. So that being said, let me think of this question with an example. Okay. But because the interface is already defined, I will quickly write it. Yeah. I don't implement it, but I just write the class for that. Okay. So this is math. So I will write the test cases first before writing the, before thinking of the algorithm, because with writing the test case, I can clarify the, data input and the expected behavior, which makes the implementation easier for me. Okay. So obviously I will first initiate the median finder. And if I add the number like say 3 first, then if I get the find median, I should get 3. And after that, if I append say like 4, this should return 3.5. And if I append 5, the median becomes 4. Then if I append say 6, the median becomes 4.5. Yeah, so this is expected input and output. Yeah. Okay, so that being said, let me think of it. So So the most naive way I come up with first is that every time I get the number, okay, so I medium find the class, or I should say medium find the instance has the array internally. And every time number is added, the number is appended to the that array. Then every time I have to find the median, I will sort it. Then find the median index number. So with that approach, so it totally depends, but the time complexity should be O1 and find median should be, because I have to sort the array, it should be n log n. Or also it is possible that I add the number and sort it as the time, and I will find the median in the constant time. Yeah. Okay. Oh, no, sorry. Because the internally the number is sorted already. Every time the number is sorted. So every time I add a new number, what I should do is, so when I try to insert the number into the sorted array, the time complexity should be O of n, because I have to shift all the following numbers of that inserted number. So that's the time complexity. And with that, the find median should be O of 1. Yeah. Okay. So however, O of n, this is, yeah, too big. And I can actually optimize it to O of log n. So let me single, yeah, optimized approach. So in this approach, I will have, yeah, instead of having only one array, I will use two heaps internally. So I will call it mini half, and also, oh, what should I say? Mini max, mini, okay. Small half and also large half. Yeah. So both of them are heap. And the thing is that basically, I will keep the number of this array. Okay. So I will give a constraint on this, I will give constraint on this, two heaps. So the first constraint is that numbers in small half is equal or smaller than large halves. So this is the first constraint. And also I will give a constraint that the length of each array, each of these heaps have approximately the same number of elements. So yeah, or only one number more in large halves. Or yeah, large half. Okay, so these are two constraints I will put on this internal two heaps. And that being said, okay, let me think of the algorithm, what happens when I add number. So when I add number, what I should do is, firstly, okay, let me think with an example. So when I try to put 3, I will put it to small half first. Then, so this comes here. then the first thing I will try to do is try to meet this first criteria. So I will currently it's okay because there is no number in the right half. So the first constraint is met. So now I will do the second constraint. So because there is one number and right half has more zero number, so I will pop this out and push it to right half. Yeah. Then when I get number 4, what I should do is firstly put it to small half. And as a result, I find that the small half has number 4, which is larger than large half number in large half. So the thing is that, so small half should be max heap. And also large half should be mini heap. So this way, I can find the maximum number in the smaller half as the log of n time. And also I can find the biggest number in the larger, smallest number in the large half with log of n time. So basically, if I try to add 4, firstly I add it to small half. Then I can find the maximum number for and from max heap and from large half, I can find the smallest number. So 4 is larger than 3, so I will pop this out from mini heap and I will add it to the mini heap. Yeah. So at this moment, what happens is that large half has more numbers than, large half has 2 numbers and small half has only 0 number. So I will pop 3 out, then push it into the small half. Yeah. So in this way, these constraints are met. So I will quickly push to small half. Then now. Yeah. Then what I should do is so after doing the second operation, so as long as the yeah so, sorry so then so I don't know in which way this happens. Yeah, I think I will take a look at the number of ranks of small half and ranks of large half. And if I find that large half has more numbers, I will, move numbers to small half. Yeah. Okay. So that being said, when I try to find median, so this is constant. So if there's the same, I will return the, average of two top numbers. And otherwise, return many in large half. Yeah. So this is what happens in find median. So I can say numbers should take all of one time. No. Log n time. Yeah. Because as I can find, so push the small half takes log of n time. And in line 29, I will move small half, some numbers to large half to, and popping out from the heap and pushing into the heap, each of them takes log of n time. And the problem is how many numbers are moved. So because both of them have almost the same numbers like this. Yeah. So if I have the, say, very, if I have the small number, I have no operation to be done to move. And if I guess some number which is quite big, which is bigger. So in this case, I have to move 5 to this. I mean, large half. So I will pop this out and add to 5. And that's it. So I can say it happens only once. Yeah. So this takes only log of n time. And in line 30, it is possible that I have to move some numbers. Yeah, but actually this is this, okay. So let me think of the worst case. How many times I have to do line 30? Repeat line 30. So probably I can say if both of them has the same number and if small number is added here, I have to do one operation. And if large number is added here, it should be like this. So I have no operation to be done. Yeah, because number length of two heaps meets the condition. I will quickly think of this case. So in this way, if large number is added, this should be moved to the here. So, and this actually meets the condition. And if small number is added, I have to move, one number to the, large half from small half. So what I found is that I had to do only, one operation at max. Yeah. So I can say log n. Yeah, or log n time. And for find median, this takes only the constant time. Okay. Yep. So that being said, let me work with the implementation. Okay. So as I said, initiate a small half. This will be used as a mini heap. no, max heap. Yeah. So because I'd like to use the mini heap, I will each element is this. And for large half, this is yeah, the heap of this. I mean, yeah, because I'd like to use it as a mini heap. Okay. Oh, so I mean, in Python, I will use the heapq library, and heapq library support only mini heap. So that's why I will, I mean, negate the yeah number of element, each element in the max heap. Okay. Okay, so that being said, if I add number first three, add two small half, I will push the small half, so self small half. Then next thing I will do is okay, if there is any number in small half, and also if there is any number in large half, and also I'm pretty sure this happens only once, but let me just yeah use while loop. Yeah, so just in case. So small half, this is the top element, and let me so large half. Okay, as long as this is met, I will move the number from small to large. So heapq heap pop self dot small half, and I have to negate it. Then I will heapq dot heap push self dot small half large half. Okay. Yep. So let me do with this. And now I will assert that ah, a bit annoying. Yeah, it's okay. Yeah, because I have to use the if statement to write this assessment. So yeah, to check if the element exists in small half or if it exists in the large half. So it's too much for just writing the assignments. It's okay. So next thing I have to do in this method is move nums between small half and large half. Okay, and because as I said, the gap of numbers is only one, so so that being said, so we need some of numbers. Okay, so if so let me rename this to, yeah, let me just remove this half names because it's too much to write. Just name it Smalls and Rajes. Okay, so if ranks Smalls, so I will pop it out, then yeah, append to Rajes. Then also I'd like to confirm that if large numbers has too many numbers, I will push out from heap pop, then I will append to smalls. Yeah. Okay, so that's a thing. And I'd like to confirm that now this is met. Okay. Yes. So I think one thing I can do is, yeah, I think I can create a method like move from small to large and move large to small method. Maybe it's useful because I do the same operation in line 4950 and in 5556. So maybe this can be extracted as a method. Yeah, and I can use it. But it's okay for now. So in find median, I will just use this. Yeah. So otherwise, both of them are the same. So okay. So this is what I should return. Okay. Oh, and one thing I've noticed is in line 50, because Raj is, oh, I have to push out. And also, yeah. Okay, also what I should do is if I push to, small of here, I have to push this. Okay. So let me confirm this with my example. So example test case. So firstly, the median find is initiated and nothing happens here. And in line 75, if I add number 3, what happens is that so negative 3. Okay. So should I do it? So if a 3 is added, this is added to here. So in line 51, first 3 negative 3 is pushed into the smallest. And in line 53, because rank of the small is 0, nothing happens. Okay. Yeah. Then in line 57, this is true because 1 minus 0 is 1. Yeah. And in line 59, rank of smalls is largest and rank largest. Yes. So in line 60, I will pop negative 3 out, and now this 3. So this has popped out, and instead this 3 is appended to push into the largest. Yeah. Okay, then in line 63, so now rank small is 0, rank largest is 1, so nothing happens. So in line 67, I could confirm that, yeah, largest 1 is between 0 and 0 plus 1. Okay. So it's okay, and line 81. Oh. I will start find medians. So in line 70, because small ranks is 0 and largest is 1, so line 70 is true. So I will pop largest. No, I don't pop it out. I just keep the smallest number. Yeah. And the same for this and this. So actually I don't pop it out. Yeah, so I cannot use number out. Okay. So in line 70, yeah, this is true. So in line 71, I will return 3. Yeah. Okay, so this passes. And in line 82, I will add number 4. So here in line 51, negative 4 is pushed into the mini smalls. And in line 53, ranks of small is 1, which is larger than 0. Rank of largest is 0, larger than 1. Sorry, ranks of largest is 1. So, and also, if I check this one, small index 0 is negative 4. So actually this is 4. And ranks largest index 0 is now 3. So this is true. Line 53 is true. So in line 54, I will pop the number from here and now it is 4, and this is pushed into the Rajas. Okay. Yeah. Then in line 57, oh, so this isn't true. Yeah, it should be 2. Okay. And in line 15, then, okay, in line 59, length of small is 0, length of large is 2, so I go to line 63, and because length of small is 0, 0 plus minus 1, which is smaller than largest length, which is 2, so line 63 is true. So I pop out a number from 3 and largest, which is 3, and I will push it into the smallest. Okay. Then in line 67, I will adopt that, yeah, because ranks of smallest is 0 and rank of largest is, I mean, both of the ranks are 1, so this is met. Okay, so in line 83, I will find the median. So because both of them of the ranks is 0, so I go to line 73, and then I will return the median average of 3 and 4, which is 3.5. So this passes. Okay, so I'm pretty sure at this moment that the code works correctly because I covered all the lines in the, I mean, class I've implemented. So I run this code. Okay, I fixed it. So in line 61, heapq. Line 61. Ah, okay. I have to push out to heap push. Good. The code was fine. So I will run this in the LeetCode platform. So you see, I have to log in. Okay, so I logged in, so I run this code. Good. I submitted. Okay, good. Yeah, so yeah, this code was correct. So I finished my today's coding practice. Okay, thank you so much. Bye.